All right, it's recording. Welcome everybody to another Danish Sound Cluster webinar. Today we have 4 special guests and the topic is about audio in AI applications. I will not be the moderator this time. Biwa, our chairman, will be the moderator. So I'll be here in the background making sure that all the technicalities are good. But Biwa, whenever you like, you can unmute and go ahead.
Thank you very much. Let me first see if I can share my screen with you. Are you seeing my screen right now?
Yes, just make it full screen and then off we go.
Okay. Yes, hello everyone. I've been looking forward to this webinar. I think AI is a very interesting theme for the audio industry. Although the audio industry is not necessarily leading in AI, there are a lot of applications that fit well into use in sound applications. And today, many companies adopt AI in the digital transformation, and they do that not necessarily because they can, but because I think most companies are finding today that it's a must that you have to start using AI because that technology gives access to a lot of things that you could not do before. I can say for my own situation, already 23 years ago, one of my companies started using machine learning in a project where we had to test small loudspeakers and find some anomalies. And there was no way that we could figure out how to do that had it not been for machine learning, which made a very successful outcome of what we did. So I have been convinced that AI is certainly a very strong way ahead for the sound industry. And AI in general, as my slide says, it's helping the businesses to become agile and innovative, and you can scale a lot of your solutions, and you can use AI basically everywhere. But it's very essential to understand, and most of you probably know that very well already, that data is the real heart of machine learning activities. Without good data, there is no way that you can make the systems work good. The basic technologies as such have mostly been developed by high-tech companies in the US, and you can see from this graph here, the orange curve up to 2019 is the business from companies in the US. I don't know if you can see the graph to the right of that, but there you can see the number of publications coming. And when you look at publications, then China is certainly coming in very, very fast and actually passing the US in number of publications. So a lot of things are also happening in China these days. We know that many Danish companies also use AI, but we are not necessarily the developers of the basic technologies. Then I would also point to that if you are entering AI solutions for your company, then cloud-based services for AI can be a very strong alternative. You can get access to a lot of computer power that you may not necessarily have in your own company. You can get access to tools that are superior to basically anything that you may have access to. You can get access to a lot of models, libraries, data that you can use for a lot of things, which can be pretty valuable, at least in a starting phase. If we look at what do we actually mean when we say AI, it's sometimes a little bit confusing, because artificial intelligence in principle is a science devoted to making machines think and act like humans. But a subset of artificial intelligence is what we normally define as machine learning, where we are trying to have computers perform a lot of the tasks without specific need for explicit programming in every case. And as a subset of machine learning, we go into deep learning, which is trying to model the human brain, the activity of the human brain with a lot of parallel activities taking place. And also in some of the solutions for deep learning, you even have some memory in a lot of the parallel processing. So this is basically how we see AI. And if you again see, I don't know if you can see that to the far right here, but we're normally defining the learning in various categories. To the far right, you have supervised machine learning, which is a pretty efficient approach that is taken by many people in sound engineering. Then to the far left, we have deep learning, which has been proving really successful in areas where you do not necessarily have full control of the data up front. So in deep learning, you can use algorithms to try to find clusters, etc., and help you generate the solutions. So, for example, if you are in insurance or in medical, then in many cases you would like to use the supervised machine learning. If you are trying to work with robots or self-driving cars, etc., the solutions will probably more be to the far left in the unsupervised learning, where you have little or no idea of what the result can be up front. Also, if we go back to the supervised machine learning, as I said, most of the applications that at least I know of in sound applications are still based on supervised machine learning. And here, in order to have a good solution, you need a lot of data, and you need consistent data, and you need to label the data. So that requires typically a team of developers and data engineers to really get control of what you're doing. So most of the time in supervised machine learning is actually spent on collecting and analyzing and processing and annotating data. And then for the training of an algorithm, we like to have a very huge data set that we can test out that the solution is working right. But labeling or annotation of the data set can be a very time-consuming job, and that in at least the applications that I've been involved in probably has taken most of the time. But in supervised machine learning, you basically try to identify a good product and describe that to the in the learning process, and then we try to identify product anomalies. For example, in the loudspeaker examples I mentioned before, it took thousands of tests to find out a data set of 300 good devices and 300 with specific anomalies. And even there, you are not having a 100% coverage. So you may have to go over in the process time and time again to improve on the data set that you use for learning in the system. But data is very essential. It's like crude oil. You need to refine the data, so you need to clean the data, and not least label the data. Otherwise, the data cannot be used. And in the labeling process, it's very useful, or I would say it's mandatory to have a domain knowledge of what you're trying to do. Even people working in the same field may not necessarily have the same understanding of a problem or an anomaly. So it's good when you are deep into the area already and you can discuss with colleagues, is this a good or is this a bad solution? But before you go into the labeling, you have to clean the data. So anything that is not really related to what you want to train your system on is removed, and then you can start labeling. And then you need to make sure that the quality of your data set is high, because if you have poor quality, again, it's very difficult to have a system learn what it should be doing and what it shouldn't be doing. And all of this supervised learning means that we have what we call humans in the loop. We use people for labeling of the data. We use people for training and validating the models. So supervised machine learning is a pretty manpower intensive process. And when you look at the labeling, how can you do that? Well, of course, you can do that in-house. And if you're in an insurance company or if you are in a health sector, you would probably prefer to do that in-house, or if you're a bank, so that you have full control over what is happening. In many cases, it can be also preferable to use outsourcing of the labeling process, to have people that are experts in labeling, but people that may not necessarily have the same deep domain knowledge as you have internally in the company. And then you have to make sure that the people you outsource to understand the process. And if you have simpler issues, you can use crowdsourcing. You can have a lot of people active in helping on the labeling of data, but usually that's for more simple solutions. Then if we go to the left of the solution set that I showed before, we have the unsupervised learning or the deep learning, where we use models that are extremely sophisticated in machine learning. And here we try to imitate the human brain through a high number of parallel processing nodes. It can be a pretty complex multi-layered deep neural network that is in use. And in some cases, for example, if it's in image application, then the recurrent neural network memory solution, where you have memory in each node associated as well, can be a very strong way forward. But still, I mean, we are trying to have machines do things, and we have very smart algorithms, and some people have very smart solutions. But when you think of it, the human brain is still superior on a number of cases that are difficult to compete against. Just think of a crowded bar at night full of people, and there's a person serving with a tray of beer, and this person wants to pass through this crowd of people. That's pretty easy for a human, but if you let a computer control that process, it's definitely not a trivial task, I can promise you. But to have the right hardware, we are also looking a lot into GPUs, the graphical processing units, where you have a lot of parallel processing taking place. And if we just have a look at the two extremes, the supervised versus the unsupervised learning, then in the supervised learning, we have not necessarily a very strong computer power behind, but we use people to interfere in the process heavily. And all the data that we try to use are annotated labeled data. If we take the unsupervised learning to the far extreme of what I showed before, we use unannotated input data, and the model is trained without knowledge of any labeling. So instead, these algorithms are trying to cluster anything in the data set and learn from that and improve from that. So I've just tried to illustrate that at the bottom. If the computer can find some patterns in the clustering, that is where it's starting to learn and working from. And in the process where we are using the unsupervised learning, basically you need very efficient computing power, and we are dividing everything into clustering, and we use the algorithms for analysis whereas in supervised learning, we use the data for predicting of things that are happening. So it's basically two extremes, but sometimes you also have solutions in between. So if, for example, you have semi-supervised learning, you can have the computer fed with a mixture of correctly labeled data and a lot of unlabeled data, and then you use the basis of the labeled data to search for new patterns and find solutions. And I just saw a few days ago that there was a new information in one of the newspapers on this chat GPT solution, which seems to be pretty powerful, where they are using, of course, very advanced algorithms for chat purposes, but at the same time they also have humans in the loop, because when you are working with human language and speech, then you do not necessarily have fine rules. So these people have used, for example, Twitter and other internet media, and really tried to look at all the data available and learn from that. So they use a combination of the two. So this is basically how we see the AI field. And now I want to move on to the presentations themselves, where you can hear about some of these very strong solutions that have been invented by some of my colleagues. And
Thanks,
yeah.
I just want to add that if people have questions, just add it to the Q&A instead of the chat. I forgot to mention in the beginning. So.
Okay. Yeah, and now we start the real part of our webinar today, where the first speaker is Torben Christiansen from EPOS. Torben, he received his MSc at DTU in 2000, and he started at Oticon the same year, and EPOS 5 years later, and he has been heading the audio engineering group in developing acoustics and audio algorithm. And today, Torben is responsible for technology development in EPOS, with a special attention on leveraging research and technology from other companies in the Demant Group. So Torben, share with us your strong knowledge in the field.
Yeah, thank you. Is it the audio coming through?
Yes.
Yes.
And also the sharing of my screen?
Everything is good.
Okay. So half of my screen is you guys, but let's see. I hope I do not cover important stuff. So yeah, so I would like to just present shortly a very high level how we implemented AI in our first product launch. Talk a little bit around some of the topics that Birger mentioned in his talk, how we went through that in a reasonable time frame with a reasonable amount of resources. And as Birger said, I'm from DTU 2000. I have actually been in the Demant Group ever since 2000, and in EPOS since 2005. EPOS was started in 2003, but it was called Sennheiser Communications. But in 2019, the Demant Group took over the ownership 100%, and ever since we have been called EPOS. And we are located out in Ballerup, so not so far from you could say, Copenhagen. Yeah, so let's ultra short about what kind of products we do. We are in the gaming segment, which most of you most likely know and have experience with. In the gaming, crystal clear communication. If you do gamings where you have a team, where you need to communicate and work as a team, it's extremely important that your voice comes through. It's also extremely important that you have good audio so that you can hear the sounds in the game. Where do they come from? This immersiveness that you are actually in the game. And then of course we make products for people who have this competitive edge. So it's a little bit more maybe more expensive than than most, but it's also what I claim a little bit better, higher quality. So it's maybe more for it's not for the totally young ones. It's maybe more grown-ups. Yeah, but it is a very exciting area to work in, and a lot of progress and a lot of new stuff also on the audio side with immersive audio. The other part we have is the enterprise segment, where we do products within the office. It's if you see all to the left, it's a product on the go with ANC, a traditional headset, but it's also conferencing, speakerphones, it's video bars with audio inside, and it's all the way to a complete meeting room where you have a control unit, etc. And if you look through these types of products, you can also imagine that audio is many different things and has many different challenges in these devices. And I know that Clément will come back to a certain differences within headsets. So I will not be around the acoustics and the challenges. So I will not dig deeper into that one. But I will take as an example how we did it for the first product where we had embedded machine learning, and that was for the Adapt 660, which is the one to the left. So we are not when we talk about the enterprise segment, there's a lot of studies done which proves that good audio matters, and that's why that's good for us, of course, because then there's a business for our company. There's a reason to educate audio engineers, the algorithm people, mechanical guys who can do good mechanics, who can do again good acoustics. So if you look at some of these numbers, it is very, very, very high numbers. And it's 68% believe that I mean, good audio can help them in a more efficient meeting. You don't have to repeat what you are saying. Over 50% has the opinion that they get less stressed if they have better audio. They understand what is said. They can much faster react and answer the right thing. 71% thinks that they are losing pitches. That means that better audio can help them in not losing out on stuff. And now I cannot see the last one on my screen. Sorry for the setup. But again, in total, the numbers they are just so big, and it just tells us there's a lot of work in front of us to do, and therefore the machine learning, the AI, deep neural networks, they are here to stay, and they require that we keep working on them because there is much more benefit, much more to gain. If you lose out 31 minutes per week due to poor audio, that's actually a lot. It's half an hour. It's a lunch, right? So who would like to miss out a lunch? So let's try to dig into what we did as a first step. And as Bill also said, it has many different categories: machine learning, neural networks, deep learning. I think internally in EPOS, when I talk to all my colleagues and engineers, the only thing it's not AI, it's not artificial intelligence. We are not there yet. It's machine learning based on neural networks and deep learning techniques in our world. And just to recap ultra short, that we then try to mimic the way the brain is thinking. And we do that having a certain network, which is pure zeros, pure no information as a starting point. And then the whole trick is, as we also said, you need to train this network. You need to have a structure that fits to the task that you need to solve. And if you take the upper left corner, if the task is to roller skating, if you need to learn that, well, then you need yeah, I mean, what would a human do? A human would go out and try it out, play, fall over many times, learn from that. It hurts. Okay, I have to stand up, keep the balance, and then get better and better. And you can see in the picture, there's also a trainer. This is the one who is guiding and telling how the improvement belongs, what is good, what is bad, especially when you go to school. You will have a trainer telling you the right things and the bad things, and you will learn. And the same thing is, as Bio said, also for the network. So if you have good data in, you have a good structure of networks, and you have some good metrics to judge if the network is doing good or bad, well, then you have a good chance to do something good. But bad data in, yeah, then you can forget about the rest. And just to illustrate a little bit what is then data in this context, and that maybe I'll come a little bit into this supervised and unsupervised learning, how we deal with that. So one thing is the target. I mean, what we would like to restore is the target in this use case. It is the microphone voice pickup of the person having the headset. So I would like to be able to communicate to my colleagues or in a Teams meeting. So the target for the system is to pick up my voice and then filter away all the noise that is around me. And these noises can be many, many things. So in order to capture the world, I need to record all these different environments. And here one key thing that we will also touch based on is this domain knowledge that you need to have. And domain knowledge is not just audio knowledge. It is actually domain knowledge. What is your use case? Because you cannot sample the whole world in all use cases. You have to focus a little bit on what is your main use cases. It is also pretty important that you know what is then good enough, what is good audio in your use case. And there each of the companies will have its own, not religion, but fingerprint on what is good audio. We strive to, and Clement will also come into that later, that we strive to have some tools that can more objectively tell us how good it is. But so far in the end, there's also some judgment of humans, what is good audio. But you can imagine that sampling the whole world, the target own voice, it can be me, but it could also be a female. So I think there's a slide later on it, but I'll just tell it now. So it could also be a woman talking, or it could be me talking very loud, or it could be, so all these kind of voice differences that can be, and types of voices, it's language that are different from country to country. You have to sample it all. You have to train a network. So maybe you train a network that is better for English, and then you have another one for Danish. Or what should your strategy be, or should one fit it all in all use cases? Some of these decisions you have to take, and that is not trivial. I think there's more. You can sample more data than you have time for since the universe started to exist. So you have to make choices here. Yeah, so what is actually the problem when we do things like that? If you have a situation like this, where people are working, I don't know if it's from home or in a library, let's assume that these two can also pick up the phone and talk. So if the target is to pick up the own voice from one of them, from the headsets, then if you train it to pick up voice, and then you train it to filter out if you are in a bar, if you are in the cantina, or if the coffee machine or the coffee grinder, all these things. And we have seen systems out there that has been trained like that. So what happens is, or what can happen is, then if the one who to the left has a conversation but is not saying anything, and then the girl opposite is also talking in her conversation, maybe this system will then pick up that girl, because that's also a voice. And therefore it's not enough just to train it like that. You also need to maybe take into account acoustics and location in the room, have more than one microphone, etc. And there is actually examples out there that you can actually try out, which is picking up the neighbor, even if it should block out the neighbor. And if we are working in the enterprise and we sell a headset for the bank industry, it is not an option to capture the neighbor talking about somebody else's private finances and problems in the headset sitting next by him. So that's a huge challenge in our systems. Yeah, but what's then how difficult can it be? As Bill also said, AI was not started working on audio. It was basically everything else almost. It was more discrete data. So, for example, for imaging, imaging has also progressed and is pretty far in more advanced stuff. But typically in image, it was object classification. So like Bill also said, you can have people pointing out where are the cats in this picture, and then you can check if your system can identify the cats in the picture. But in audio, it's not the same, because in audio, you have to identify the noise, which would maybe be the cats. You have to take them away, okay? And then you have to predict what's behind the noise. What if you remove the noise, what is then the correct speech or audio signal behind that? And as you can see in this image, it's not trivial to guess what is behind these cats. And now you have not trained on this, but still, yeah, I hope you can see that who would guess that this is behind it if you have not seen the picture before. Yeah. So let's move on to if we talk about the supervised and unsupervised learning. There is, Bill, you mentioned some very outliers, totally in one end and totally in the other end. I'm not sure exactly where we are with what we do, but one way of doing something that is at least less work heavy is that if you record the target voice, you record it with different languages, age, vocal effort, gender, and loudness. Then you do other recordings with different voice noise scenarios in a high quality manner. Then you can mix them together. So you can take a male talker in a train, or you can take a female talker in a train, and therefore you have labeled stuff. So you know what should the target be when I separate this male talker in a train. Well, it should be the male talker again. And then you can try to figure out how to measure the distance from the target and give that a certain metric, and then reward your network or punish your network if you are guessing too crazy. So basically the task is mix these two, clean it up so that you get back to the voice. Very, very easy. And Clément will show you some examples of it. And in this system where we had the ADAPT 660, what we have done there is we have also used the spatial knowledge that you can have if you have more than one microphone. You have beamforming that you try to zoom in and focus on the mouth. You have to remove some echo that could come out of the speakers. And you have some noise reduction, a single channel noise reduction on top of that one, removing the last noise. And then what we have done in EPOS is to put something on top of that one so that we can control all of these parameters. And the network we put into this one, the platform back then, it could not contain the biggest network in the world. So we had limited of space and memory, especially memory is a constraint many times. And so we have a limited amount of parameters that we control. So we have decided to use this EPOS network to control some special situations that we would not trim the traditional algorithms. We would not trim, especially for these outlier occasions. We would trim them for good audio in the normal use cases. And then the AI network helps us sometimes when the environment gets totally crazy and the normal parameters is not working. So, and it works in the frequency domain. You have the mixed signals, and then this is a very, you can say very 100% correct result. I think it will never be like this, but you have the mixed signal, you then remove the noise with the help of the network, and then you get the clean speech afterwards. Yeah, and then just to brag a little bit, this for the UC world, this was the first headset in the world with embedded machine learning in the audio path. There has been a lot of machine learning applied for word recognition, Alexa and other stuff before that, but to apply it in the signal path, that was new back in 2020. Future work, just to touch a base on that, we are still here, day one. We would like to clean up the speech better, and we have done before. And we have not ended that journey. There's a lot to do still, but you could imagine that that in the future you could get closer to the user. You could use, with the help of the user, you could fit it better to the user. And maybe these two, they will work in parallel. So you could imagine if you have your mobile phone and you have to teach it your fingerprint, you have to put on your finger 10 times. This is not training of a neural network from scratch. There's a prototype of a neural network that knows the fingerprint structure, and then you train it a little bit more in the direction of fitting it to you. And how could we do that in audio? That is some part of the future stuff. And then it gets more crazy in the future if we want to, is to analyze who you are. People are also working on like the fingerprint and the eyes, also using the biometrics of voice to identify who you are. And maybe these three together will have higher security than only one of them standalone. It can go more crazy. It is, how are you? So if I could detect on your voice if you are talking like this and you are maybe you are getting stressed, maybe you need a break or something like that. Before I would recommend that for our users, I think we need to do some more work and research to be sure that if we detect that people are stressed or need help, that we are also sure that this is the case. You could also just be exhausted because you were running up the stairs. Last thing is also, I mean, then we get to close to AI, I think. Then what is it that you want next? When you say this, when you do that and combine a lot of metadata also with audio, how can I help you with the next step you want to do, which you have not told me yet? Yeah. And I think that was it. And that I think by ending this session, I think it was a very, very high level overview. And now both Clément and Lars is ready to go a step deeper. I don't know, Bill, if you want to say something in between.
Yeah, thank you very much, Torben. It's a pretty good overview you gave to the solutions you have been working to. If people have questions, then use the Q&A, and we'll get back to questions at the end of this session. And then we move on to our next presenter, which is Clément Laroche. Clément is a senior research scientist in audio research group at Jabra. His goal is to improve the voice pickup quality by combining machine learning and traditional DSP algorithms. Clément graduated from Télécom Paris in 2017 with a PhD in computer science, signal processing, and machine learning. And I'm pretty sure that Clément will take us on a journey where we can hear some examples of what can be achieved. So Clément, go ahead, please.
Thanks, Björn, for the intro, and thanks, Torben, for the introduction also of the field that we are all working on. So let me try to go full screen, and I'll take on. So I'll make a speech today on a data-driven and AI-based algorithm for speech enhancement. Of course, this AI is a little bit of a buzzword, but bear with me for this. It's just to, let's say, bring in more people. So just a little bit of few marketing slides to begin with about GN. So let's say GN is a company that's split in two branches. One is more specific to the medical side, GN Hearing, and they make a lot of hearing aid and hearing instrument. And then we have GN Audio, where I'm working, where we do headset for office workers, for remote workers, and also for consumer. And I've been working in this company for 5+ years now. I started in 2017, and I'll give you a little bit of an overview. So our product range is pretty broad. As I mentioned, we have a lot of different headsets, a lot of different form factors, and that causes a very specific problems, because all of these headsets have a specific use case. So we can have, let's say, this headset for call centric. So in call centers that people use 8 hours a day, and they need to have a very good sound quality because it's really a tool that they use constantly for their work. Then we have maybe headsets which are used a little bit less for office workers, people that work from home or work on the go, as they say. And then we have audio for consumer, where it's mostly for listening to music and answering a few calls here and there. There are also speakerphones, and these are also, they have a different use case and specificity. So this very broad range of products makes the challenges very interesting and very specific. So I want to talk about two data-driven approach, and the first one is denoising that Torben mentioned before. And so denoising, what is it? So let's say in the case where we have only one microphone that can be placed on our headset, and we are trying to have a communication, use this microphone for communication. The microphone will pick up the voice of the user, but it will pick up also all the ambient noise and background noise that are in the environment. If you work from home, you can have the dog bark, you can have the baby cry, some noise from the street outside, and this is not good for communication. It can make you sound less professional. So it's very important to try to clean that as much as possible. It's a very big topic also for all these big players. So here, Google Meet, Teams, Zoom, Skype, etc. They all have their own denoiser in their product, so that you can, let's say, improve the sound quality. If you're not using let's say, a professional headset, they can provide with denoising and help you with improving the sound quality. For us in our headset, it's also very relevant, but we have let's say we have a little bit like an edge on them, because we really are located on the user's head, and for example in this case, the microphone is on a boom and it's close to my mouth, so it picks up the sound of my voice much better than if it's on my computer sitting, let's say, 50 centimeters away. That's a big difference. Still, it's not difficult, so it's not easy. Sorry. So let's say. Neural network need data, and we show that we have a lot of different headsets. So how can we have data for training this neural network? The problem is that training on real data is not really feasible. So let's say we want 200 people talking in 100 different rooms. Each person needs to take 10 positions in each room for diversity of acoustics. And then we want to have 25 different background noise in each room. That's a little bit impossible. That would be a little bit what it looked like if we wanted to have recordings in Jabra. So a lot of people queuing up to record a Jabra dataset, and then assuming you change the device suddenly, you have to redo that all over again. So that's unfortunately not possible. However, we can use simulated data, and by that I mean that from an audio, what I would call an audio simulator. So that's basically a good understanding on acoustics and on how the device are built. We can simulate a lot of audio recordings. And that means we can simulate room acoustics. We can simulate, let's say, different speech using different database. We can simulate a different use case from, let's say, different device, speakerphone or headset or truly wireless products, different device configuration, multiple microphones, and different noise with a lot of different, let's say, noise database. And this is great because it allows for a much faster and cheaper way to generate our audio data for training the neural network. And it's also very flexible to geometry change. If the designer of the product suddenly comes up with a crazy design where the microphones are located in different position, you can modify the microphone placement in your simulation and rerun it again. So it's fairly flexible here. You can it's adjustable for debugging. So what I mean by that is if you made assumption on your simulation and these assumptions are maybe not correct, then you can come back and improve the quality of your modeling and generate data which is more realistic. And let's say, of course, in this day and age, it's very important to mention it's eco-friendly. You will have less prototyping, less e-waste, and of course, it goes hand in hand with the fact that it's cheaper, so it's great for a company perspective, and let's say for academia as well. So that's a little bit on how this data is generated for training this neural network. And a quick example on simulation. So let's say I've taken 3 products from our line. So one is a headset where we have a microphone close to the user, like what I'm using at the moment. And I want to basically separate 2 use cases, and the second use case is the truly wireless. So it's when these very small earbuds like the Apple AirPod Pro. I'm sure people are familiar with this. And here it's basically I'll make you listen to 2 examples. One is recorded by one microphone close to the mouth, and one recorded by one microphone close to the user's ear. And so, yeah, sorry. Let me explain a few more things. So the problem when you put the microphone further away from the mouth is that you get a lot of reduction in the sound that's being picked up of the user. So basically, from going to a microphone close to the mouth to a microphone close to the ear, you lose around 12 dB. And because the background noise is picked up exactly the same, depending on whether your microphone is close to the mouth or close to the ear, then it means that your signal to noise ratio will be much lower. So for the sake of time, I will not make you listen to all these examples, but just 2. So one is the recorded signal in a noisy environment with a microphone close to the mouth, and one with a microphone close to the ear. So let's listen first to the microphone close to the mouth.
And the people sought to overthrow the government. Then Napoleon was called on to protect the palace of the Tuileries, where the offices of the French government were located.
All right, and then let's listen to the one where the microphone are located close to the ear.
And the people sought to overthrow the government. Then Napoleon was called on to protect the palace of the Tuileries, where the offices of the French government were located.
So let's say in exactly the same environment, you can see how much more difficult the task is when you are using this tiny earbuds compared to when the microphone is close to the mouth in terms of denoising perspective. So starting from there, okay, let's see how we can train this neural network to improve this speech quality. So from the data that we simulated before, we have the input data, which is a mix of speech plus noise, and that's what the neural network will process. And the neural network will basically try to predict, let's say, some features and a filter, for example. And this filter will try to remove, let's say, all the information which is noise, basically, and try to keep the voice as clear as possible. Try to limit the amount of artifacts that's in the speech. And once the network predicts the speech, we can use the clean data, so that the user voice without the noise, as Torben mentioned before, and we can compare basically the output of the neural network to this clean speech, and compute a loss. So basically, tell the network how good of a job it does at improving this speech. And this loss function will basically also help us to slowly, through a stochastic gradient descent, to slowly tune the parameter of the neural network in order to improve the quality of the speech iteratively. With hundreds of thousands of audio example, you can refine this prediction until you have a good sounding speech. And let's say another detail is that, of course, denoising is really, you have 2 mechanisms in denoising. One of the mechanisms is what I would call a VAD-like denoising, meaning that you have first to detect when the user is speaking and when the user isn't. And when the user is not speaking, you can be quite aggressive with your denoising, so you can almost cut the entirety of the signal. However, when the user is speaking, if it's only that, you will let the whole noise through and it will not sound so good. So then you also have to be very, very good at denoising when the user is active, and it means that in between the harmonic of the speech, you have to be very precise. Otherwise, you will introduce some artifact. And these artifacts you will hear in the examples that I have lined up. All right, so then how good can it be? So from the two recordings, I've processed them through what I would consider something close to state-of-the-art neural network for speech enhancement for a single microphone. So let's listen to the noisy and the enhanced file for the two different form factor. So that's the noisy.
And the people sought to overthrow the government. Then Napoleon was called on to protect the palace of the Tuileries, where the offices of the French government were located.
And enhanced.
And the people sought to overthrow the government. Then Napoleon was called on to protect the palace of the Tuileries, where the offices of the French government were located.
So it does a good job at removing the speech, and you don't hear a ton of artifact, even though there are still a little bit of noise in the background. And let's go for the difficult example, very difficult example.
And the people sought to overthrow the government. Then Napoleon was called on to protect the palace of the Tuileries, where the offices of the French government were located.
And enhanced.
And the people sought to overthrow the government. Then Napoleon was called on to protect the palace of the Tuileries, where the offices of the French government were located.
All right. So the second example, because the SNR is much lower, you can hear the neural network trying its best, but also introducing some artifacts. And yeah, so that's of course the drawback of having this very tiny device with a microphone very far away, is that the task becomes very, very difficult if you only have access to one microphone. Let's also what I would like to talk about is so the second data-driven approach is speech quality prediction. So you heard some example of speech enhancement, but now I would like to evaluate how good of a job the speech enhancement method has done in terms of improving the speech. So usually what's done is that you have a human listening test, and that's let's say the gold standard. You will usually ask a panel of experts to rate this different audio example and rate the score between 5 that will be excellent and 1 that will be bad. But this is, let's say, very cumbersome. It's very expensive because you have to pay these people that give their time, and it's also very slow as people are very busy and they don't have time to answer this listening test all the time. So one way to do it, how it's preferred in the literature, is to use what's called intrusive methods. So if you have access to the clean reference, which is usually not the case in most cases, you can use this clean reference, compare it with to your noisy or enhanced/degraded file. You can compute some sort of mismatch between the clean and the reference, and you can map this difference to a MOS score. So the same MOS score I presented before, from 1 which is very poor to 5 which is excellent. But then the brain, humans can usually do not need this clean reference in order to rate an audio file. So the idea is, well, can we mimic the behavior of the brain, let's say of human? Can we mimic that with a neural network? And there have been a tremendous amount of work in this area that's called non-intrusive speech quality prediction. And they say non-intrusive because you do not need a reference. So now you can directly take a noisy signal, give it to your system. It can be a neural network, it can be something else, and you can predict a MOS score from only the noisy signal, and that's very good for many reasons. The idea is that well, if you have access to that, you do not need label, so you can directly predict the speech quality of your test signals, and you can go out in the field, do some recordings, and have access to this clean to these MOS scores. So the basic idea is that we want to introduce a method that will take, let's say, quality label. That will create quality label from intrusive methods, and then we want to train a non-intrusive model that predicts these speech quality metrics. And for this purpose, we use the vScore, which is a quality metric created by Google, and doing basically what's been done in the literature, we try to create a non-intrusive metric for that. And the idea is that then you have to create the data. So exactly as I mentioned earlier, we have access to a lot of clean reference speech. That will be our reference speech. And through our audio simulator, we add some noise, add some reverb, add some enhancement from, let's say, different device, different enhancement models that we have worked in-house. And we create, let's say, a lot of MOS values from this vScore system. Let's say we generate 100,000 files where we'll have the noisy and the MOS score, the related MOS score. And then from that point, when we have generated the data set, we can discard the clean reference. We don't need that anymore. We can discard the vScore system. We don't need that anymore. We already have the target. And we can train a neural network to take as an input the noisy file and predict the MOS. The predicted MOS will be compared to the target MOS, and through the same system as before, you can optimize your neural network to try to give a prediction which is as good as possible. And this has, some hypothesis. So this means that, of course, we assume that vScore represents quality well, and that's, of course, up to debate, but I will not discuss that at the moment. And so, yeah, for result, the system works. So let's say if we look at the training distribution, so if we look at the data that was made in a similar way as in training, we can see that the mean square error of the prediction model is pretty low. So it means that the system is able to predict vScore up to a very, let's say, fairly high accuracy of 0.1 or thereabout vScore point, which is very good. And then we used, let's say, a bunch of different distortions, so different speech database to try to see if the system generalized to a different speech. We tried to use different noise database to see if the system generalized to different noise and different distortion, different miscellaneous distortions. And then we could see that most of the time the system would generalize fairly well. Of course, there are some other distortions that were not very well represented. And then that's touching on the problem of generalization, meaning that if you didn't include all the possible distortions or, let's say, things that the model will encounter in real life, then your model will not perform very well. So for example, unseen distortion. So if the model never saw codec distortion and the package loss distortion, and if you provide signals with codec distortion or package loss, it will sound pretty bad for a human. But because the model was not trained on this distortion, it just over predicted and basically said that the quality of the sound of the speech was much higher than it actually was. But this could be rectified by just increasing the diversity of your training data, hopefully. And that's the main problem of machine learning models is the generalization. So let's say very quick conclusion is that really neural network are able to do a very complex mapping. Predicts things that human can, let's say, for speech quality. So that's great, and they can generalize well to some unseen conditions, but not all of them. So there's still a lot of work that needs to be done in order to improve the quality of the simulation and specifically also to understand a little bit this black box system, which are quite difficult to interpret. And finally, the main problems that Torben mentioned was that they require a lot of compute, and for edge application, it's usually very difficult. So hopefully regarding that, we have some open position for a PhD. I will do some small advertisement and then I will give the mic away. But we have an open position for for a Convol project, so European project on audio application for ultra low power processors. So you have my email address. Feel free to send me an email, and I'll send you the information about this to hopefully bring this cool neural network into edge devices in the future. So yeah, thanks a lot for your attention. I will give it back to Björn.
Thank you very much, Clément. It was interesting to see the depths of the work you're doing, and you even managed to get some advertisement going. Excellent.
Yes.
Next in line is Lars Bramslöv. Lars has a PhD he's a principal scientist at Erik Holm Research Center, which is part of Oticon. Lars holds an MSc and a PhD degree from the Technical University of Denmark, and his PhD work was carried out at Ericsholm. Lars has 30 years of extensive experience in acoustics, in hearing science, and in hearing aid research and development, including employment at the House of Air Institute in Los Angeles, and he has been working at the Oticon headquarters at Smørum in Denmark. Lars is currently working on the application of deep learning algorithms in hearing healthcare, and he also is a current president of the Danish Acoustical Society. So Lars, please go on with your presentation.
Thank you, Björn. I assume you can hear me and see my slides?
Yes.
Perfect. Let's get on with it. I have a very nice fly-in now from the three other gentlemen, so I think you will have to bear with me that it's going somewhat fast, but we've learned a lot already, and some of this you're already familiar with by now. Let's think about forwarding the slides. Let's see. Just a moment. Here we go. If you think about how signal processing is handled in hearing aids and in other audio devices for that matter, how we used to do it and how we do it now is quite different approach, as you've already learned. See, in the old days, we did algorithms. We programmed them, we made filters, we specified them, we made some rules that we thought would make sense for real sound environments. And we used all of that insight to solve the task, and that could be, for example, beamforming, noise reduction, and what have you, as you have in all these modern audio devices. But to the right, you have the new approach where we use artificial intelligence, or whatever we want to call it. Like the other presenters, I'm not too happy with artificial intelligence as a term, but it's here to stay. I call them dumb machines. But anyways, with these approaches, you have to use some kind of encoding. You have to decide what features to present to your deep learning system. Then you have to think about what training algorithms you're applying. And you are actually you're required to more think about how you select the right examples. And we've seen plenty of examples of that already from Clément and Torben. And of course, you also have to think about what are meaningful evaluation criteria, or as it's called in deep learning terms, what is the proper loss function to apply to get at the best possible goal. But I promised to tell you about deep neural network in hearing devices. And let's think about an imaginary device. I hope you can see my pointer here. Yes. An imaginary device, a hearing device, which has multiple microphones to do acoustic scene analysis of what's going on. It can do beamforming of different kinds. We can segregate these streams. We can select some of them perhaps and amplify them and present them to the user. And in this future example, you have EEG feedback. So the instrument is actually able to read brainwaves, EEG waves from the listener and use that to select particular audio. So in other words, selecting a target voice or what is interesting at the moment And then we also have this element called cloud training. Let's get back to that. So we can apply deep neural networks here for separating the different voices if they were coming from the same location. And I'll give you an example of that later. We can also use the deep neural networks for noise reduction, speech enhancement in a more traditional way. And we can also think about using them directly for hearing loss compensation as you would do in a hearing aid. I'll get back to that as well. With respect to these EEG signals, they are very hard to decode and interpret, and that's still a huge research topic. And also here, DNNs are being applied to process the brain signals, typically in a supervised manner, to try to find out what is the intent of the listener? What is it that the listener is attending to at the moment? DNNs are also being used for sound environment classification. That's also a popular application to decide, is the user listening to music, speech and quiet, speech and noise, sitting in the car or what have you, and using that to change the settings of the device. And finally, the DNNs are helpful for optimization of settings from large data sets. And by that, I mean, how can we get better settings, hearing aid settings for the individual user based on both data collected in the field from that user, but also on data collected from other users. And then there are, on top of that, some, you could say, more classical applications that could be applied in hearing devices and possibly are for speech synthesis and for speech recognition. So let's look at the first example using a small deep neural network for noise reduction, and that's what's used in the available Oticon More hearing aid. So here is the marketing slide for Oticon More. The DNN processing here is called neural clarity processing. And so to provide more clarity and better contrast. And let's look at that. The idea is to apply post-filtering based on a deep neural network. So it's replacing what's called the post-filtering part of many typical so-called MVDR beamformers. So the idea is, just as has been mentioned already by Clément and by Torben, that you have a target sound, you mix it with the noisy sound, but you apply some gain, smart thinking, you apply some gain to the noisy sound and compare the output, and then you use that to update. So that's during the, well, you have the target sound available when you do the training. Once you've done the training, the target sound goes away and you only have the noisy sound, but you're applying the gain to provide a better quality or better SNR than you used to have. But how can we train the DNN to act like a meaningful post-filter in real scenarios? Well, you've also heard what this is all about already. In our case, a lot of sound scenes were captured in a spatial manner with a so-called spherical microphone, lots of different real environments, and they were all combined for training the system to provide the best possible post-filter gain. Something that is better than the conventional rule-based. Of course, in our business, we need to test these things and document that there's actually a benefit from the things that we do to the speech signal. And here you have the results of a matrix sentence test that was performed at Oldenburg. And it looks like this. And let me just walk you through a little bit of the slides. The hearing aid 1 is a traditional post filter, and the hearing aid 2 is the DNN-based post filter. And what you can see in all cases is that either in the off situation, there is a difference that's not so interesting, it's not significant. In the post filter only, that's where we want to compare the DNN-based with the traditional one, the conventional one. You see there is a significant difference between these two. So there is benefit there. On the order of roughly half of dB. If you do a technical measurement, there is a difference of 2 dB, but the speech test done on users gives you a difference on roughly half a dB. And likewise, if we add the beamformer to that, we get even more improvement in the speech reception threshold. The axis here goes minus because minus is better. So the higher you are on the axis here, the better the user is performing with the device. So that's the clinical documentation that's available for this feature, and that's already available in instruments. So DNN is here already, as you also heard before. It's trained by example rather than rules. It is a small deep neural network. That's what's possible right now in current hearing aids to fit in. But we see that the DNN is better and smoother, slight spelling error. The DNN is better than, and the gain functions are smoother compared to the simple traditional rule-based noise reduction. So we get better speech intelligibility, but we also get better speech, better sound quality. And is this now the end of the story? No, well, you can think about using deep neural networks for voice separation. And in this case, it's a larger deep neural network. And this is some research that we did together with Tampere University. What we do here is we have a spectrogram of the mixture. You have the mixture coming into the system. You calculate a spectrogram of the mixture and feed that to the deep neural network. The deep neural network applies what I have shown here as a sieve, what's really called a ratio mask, to find out which parts of the input spectrogram is assigned to source 1 and which parts are assigned to source 2. And in that way, we have separated two voices. These are two voices that are inquired. We have separated them, and we can go back from time frequency domain back to the time domain and hear the audio. We can do that with a delay of only 8 milliseconds. So the latency or the processing delay of this algorithm is only 8 milliseconds. And that's really crucial for hearing aid applications where low latency is crucial, in particular if you have so-called open fittings with an open ear canal. So here's an example of what that sieve might look like. This is the ratio mask required to separate speaker female 2 from a mixture of female 2 and females 3. And the upper half, what you see there is the ideal ratio mask. So that's knowing the two signals. And so it's basically just the ratio of the power of the two signals calculated in each time frequency bin. And once we have trained our system with that, we can then apply the mixture again to a trained deep neural network, and you get something like this. This is the estimated mask you see in the bottom half. And you can see they are somewhat similar, but not nearly the same. And yet still, we actually get a quite good performance. Let me play you an example here. Just a moment. Here we go. This is the mixture of two male voices from the Danish hearing and noise test. These were known in the training, but of course the particular sentences here were not used in training, but only in tests. So here's the mixture.
Min kuglepen skriver med rødt.
I hope you can hear that. And turn up your headphones a bit if it's too soft. Two males, so let me play it again.
Min kuglepen skriver med rødt.
And I've shown it on top. Visually, you have these two sentences on top of one another. And we're asking listeners to repeat either one voice or the other. So here's the male as it comes out of the algorithm, male 1.
Min kuglepen skriver med rødt.
Oh, that was not the right one.
Posen her til grøntsager.
That's male 1, and male 2 is here.
Derhjemme spiser vi ikke kød.
So you can hear it's actually doing very well. You only hear a very faint version of the competing talker.
Posen her til grøntsager.
And the reason for this is that when you have two voices and there's no background noise, then there are actually lots of glimpsing possibilities where one time frequency bin of one voice dominates over the other voice.
Derhjemme spiser.
And let me show you some results here. We tested this on three different algorithms, three different DNN algorithms, feed forward, a long-term, short-term memory network that has some latency built in, and a convolutional recurrent neural network that has even more latency built in. They are all on the order of 3.5 million weights, so they are more than what you can fit in a hearing aid today. The sum, that's the unprocessed mixture, gives a word score on the hearing impaired listeners on roughly 50%, slightly above 50%. When you go to these two different DNN conditions, you get to the range 60 to 70%. And the separate, which is the ideal, is 75%. And this is all in a case where both voices are available to the listener. One goes to one ear and the other goes to the other ear. So that means they are free to attend to whichever voice they want. And you can see there is an improvement here from the processing and the separation. And the improvement is on the order of 13 percentage point, which in the hearing aid world is actually quite a relevant and useful benefit. And even with a perfect system, we wouldn't get any better than the 75% that you see. If we then choose to just use one target as the output, so we're just eliminating the other and only presenting one, you can see we get very dramatic improvements going from a little below 60% word score to almost 100% word score. So that's a 37 percentage point increase, much, much better. But this will require that the device can somehow select between the two target voices. So that would either be guided by, say, eye gaze, or by choosing one voice or the other on an app. And you would have to control the system that way, and of course rule out the other ones. You cannot switch attention very easily in this situation. Then a newer type of application of DNN is something we're looking on now in a more experimental way. We're using deep neural networks for hearing loss compensation in combination with auditory models. So what is an auditory model? Well, it's a computational model of hearing. And there are two different ones. The one to the left, you may have recognized it from Torsten Dau and his research. That's a psychoacoustic model. So it's based on behavioral function of the, in particular, the inner ear, but also parts of the brainstem. So it's based on psychoacoustic experiments that have then devised this type of calculation model. And the point is you can actually simulate a hearing loss here. So you can either have normal hearing or you can have hearing impairment in the model. To the right is an example of a more physiologically based model where you can actually recognize some of the elements of the physiology of the cochlea, the transmission line of the basilar membrane, inner hair cells, auditory nerve, and you use that to simulate hearing with normal hearing or with a hearing loss. And then the idea is to take this two models, you could say a model of the ideal hearing and the model of deficient hearing, as determined by for the individual user, and put in this compensation model in between to try to improve the signal. Feeding, so that's like the hearing aid, you could say. That's the hearing aid we're trying to build here. That's going to the model of the deficient hearing. The output of that is compared to the model of ideal hearing, and you get a difference here in a perceptual or physiological domain, and you use that to feed back through your deficient model hearing and back to the compensation model to update the compensation model. This was the classical backpropagation in a slightly more complicated manner, and by that you can create an enhanced signal that compensates for the hearing loss. So more to come on that, but not today. Then there's the question: these larger networks that I mentioned, how do we get there? Are we there yet? Do we have enough processing power? Not quite. So we have to balance the performance and the power saving. Performance, we want to do well in unknown voices, unknown noises. We want good sound quality. We want good speech intelligibility. But When it comes to the power saving, of course, there is a cost for DNN parameters. The more power, the MIPS, the calculation power, and the topology also have an implication on the power saving. And that's something where time is on our side, both in the sense that we are improving the algorithms, and in the sense that as the years pass, we're getting more and more power for the same number of milliwatts. You could also think of having an external processor. There's actually one of our competitors, Whisper AI, who has such a solution, where you are putting the computation power in a black box that goes in your pocket and is doing all the heavy processing, and then you have to stream wirelessly from the ear level devices to the processor and back again. I think that's a quite clumsy solution, but that's one way to do it. And of course, when you do it that way, there is an additional delay from the wireless transmission alone. But time is on our side. We're getting smarter networks. We're getting more processing power, as I just said. How about deep neural networks for better settings? What is that all about? Well, that's also being applied already today by actually multiple research groups. There is a figure here that illustrates what this is all about. Well, it's about collecting data from the device and on the user. So we're collecting data in the real world. We are also collecting not only sound data, but say physiological data, pulse, heart rate, weight, perhaps, different things. And we can feed all of that, perhaps also some ratings from the user in the environments they're in. We can feed all of that to the cloud together with data from other users and use that to train on this large data set, and via our research provide even better settings in the devices. And that's only talking about the settings. That's not necessarily the signal path. So you can say that's not so far away when we're talking about the computation power. So what is AI? Are we talking about AI here, or is it hype or what? Well, I sometimes call them dumb machines instead. They can replicate by known examples, but they are never better than the chosen training examples. On the other hand, and that's why we're in this business, they are already now outperforming the old traditional solutions. But generalization is a challenge, as you heard before. In the hearing aid world, we have to provide true benefits. We have to provide clinical evidence, which also takes time. And of course, then there is the computation power and the size to think about. So summary, small DNNs are already used in hearing aids using smart noise reduction. They are outperforming traditional solutions. But there is further potential in many areas: voice separation, speech enhancement, hearing loss compensation. But the AI is here to stay, that's for sure. We'll continue our work in this direction. So thank you.
Thank you very much, Lars. Thank you to Torben, Clement, and Lars. And now we just have a few minutes where we can try to answer some of the questions that have come in from you. There is one question here from Lars Lindahl. He says, it's a question for Lars. How does the model perform with unheard speakers? Lars and Jens also said, did you see an increase in word score between the separate and single target speaker within the sum case? And do you have any idea why?
Lars,
Oh,
can you
that's
stop
a lot
sharing
of
your
good
screen,
questions.
please?
Yeah.
I'm sorry.
Can
Should
you
we take
stop
the
sharing
first?
your screen, please?
I will. Those are some good questions. I'll take it from the top. In this particular case, I wasn't so clear about that. In this particular case, there are only known speakers. So I couldn't answer specifically your question on, but we did do some simulations using objective metrics of speech intelligibility. And of course, we saw a degradation when you go to unheard speakers. So there is a drop there, but there is also still a benefit. Then the question about the it's correct that there was a slight increase in word score between the two cases, the dual target and the single target case, for the sum condition. I don't have an idea, and honestly, I don't think they are statistically significant, the difference between the two. So I don't think there is a difference, but I would have to go back and double check. And the delay for the different models, well, actually the processing latency is exactly the same in all three cases. It's the 8 milliseconds that I mentioned. The only thing you could say is that the LSTM and CRNN networks have a longer, not latency, but they have a longer memory. So they're looking further back in time. The latency is really how much you're looking forward in time. And that's only the 8 milliseconds that I mentioned.
Thank you, Lars. We had several questions. Some of them disappeared for me, but I can see there was one from Kamho Erkut. And he asked, and he said, thank you for all for giving a nice intro on model or data-driven audio approaches at your companies. How would you characterize your machine learning lifecycle management as defined by Google? There's a long link to the Google, where you have a level 0, which is a manual process, a level 1, which is a pipeline, semi-automation, or a level 2, continuous integration, continuous delivery, pipeline automation. So I think this is a question to all three of you. Torben, would you like to chime in on this?
Yeah, I can start. We are quite early days. Of course, it's structured, but maybe level 1, without knowing exactly what the definition is. I think we are still struggling to get the energy about all the tools around it. In the end, we need people to maintain it. I mean, it's almost a full-time job just to maintain all the tools around it. So I think we are in the build-up. It's not completely 0. So let's say hopefully a 1.
Okay, very good. And Clément, would you have a go on where you are?
Yeah, I think it's why I responded in the chat, but let's say GN as a, let's say there's a lot of AI ML application in GN, and some of them are at different levels of maturity. So some of them are maybe more towards the 2, some of them are more towards the 1, and some of them maybe more research oriented, less mature, are more towards the 0. So yeah, we are a big organization, and many people are working with AI in different areas, and yeah, so that would be my answer.
Oh, that is a pretty good widespread approach, which I think is pretty realistic for many larger companies. And Lars, would you have a go on where you are? You probably do.
I don't remember the exact definitions, but for sure we are looking at a closed data set both for the training and the testing right now. In other words, we're not continuously updating our models with new data. Of course, that would be the case in the future, and I think that's what you called continuous integration or whatever it was called.
Right.
But with the processing approaches that I showed, we're only dealing with closed data sets now. Is that a level 2? I think so.
Close to. Rasmus Klitt Mortensen has a question to Torben. He says, can you disclose what kind of models you use for noise reduction? Is it a CNN through all layers, taking and outputting spectrograms, or some recurrent model?
Yeah, I cannot go closer to that one, but it is yeah. I cannot go close. But
okay.
there is some patents out there. So if you do some intelligent searching, you might find out.
And Paul Margron has a question for Lars. What kind of hearing loss are you modeling, trying to compensate for in your DNN approach? Isn't it more straightforward to directly invert the hearing loss model to get the compensation and therefore the enhanced signal if relevant?
Yes. Yeah, I know Paul. Hi, Paul. Good question, Paul. Well, if you think of simple models that are used for hearing loss, such as loudness growth models, these are typically the basis behind the multi-channel compression that you have in all modern hearing aids. And that's a direct inversion, if you will, but it's a very simple model, the loudness model. These full-blown auditory models we're talking about here are highly nonlinear beasts that have many channels. So the whole idea is to try to have the DNN learn entirely new ways of processing the signal to get a better hearing loss compensation than we can in the classical approaches. I hope that answers the question.
And one more question for you, Lars. It's Va Nogueira. The question sounds like this: any potential issues regarding user data protection when recording the environment using the hearing aids for online training?
Yes, I assume this is Waldo. If so, hi Waldo. For sure, this is something that needs to be dealt with in the future. If you decide to use a system like this to enhance or suppress your spouse, depending on your choice, then of course there is a confidentiality aspect on the recording and uploading of these data.
And I can't help.
Can I comment on that one as well?
Yeah, definitely.
Because
Go
I
ahead.
think, Bjørn, you have also earlier pitched when we have been out there and talking that this is a very, very good question, and it's highly relevant for the future if we would like to personalize our neural networks when we get more computational power so that we can do it live. It would clearly be for the benefit of the user, but how do we make them trust that we don't have a misuse of the data? So I think currently we are maybe estimating signal to noise ratio, which is not revealing a lot, but we would like more details also in the future. And how do we do that so that our users trust us? I think this is one of the most important things for us as companies to make us trustworthy and not like others. You could say the big ones, they might not be trusted so much. And how do we do that? We have to find out. Lars has a comment.
Yeah, maybe I can add that there are approaches now also with smartphones where part of the training data, the personal training data, is kept local on the phone, on the personal phone. So you can have these distributed types where you're only uploading, what can I say, anonymized data, but keeping the private data on the phone. This distributed model can also address the problem.
But for sure, we are moving into the ethics of what we are doing with these new technologies.
Yes,
and I'm pretty sure that we will have a lot of discussions in the future on how to go along. I can see time is running, and we're already 3 minutes beyond the stopping point. So I think it's my duty as moderator to stop a very interesting discussion here, although I would have liked it to continue a long time. So I would like to thank my three speakers here for some excellent presentations, and also thank a lot of you users, or you people out there that have sent in questions. We didn't have the time to answer all of them, but I hope that you somehow can get through to us in future events and ask your questions. And please do not forget, there will be a questionnaire coming up to you after the event. Please give your ratings on the event. It's very important for us so that we can improve on what we're doing in the future. And with that, I think we are getting to a close. I would like to thank all of you. Have a Merry Christmas and a Happy New Year, and hopefully see you on board some new webinars in 2023.
Thank you.
Bye-bye. Thank you.
Bye-bye.
Bye-bye.